is our speaker this week. He is an assistant research faculty member in CyLab and in ECE, and he's doing a lot of different projects related to security and usable security. And so today he's going to talk about one of his projects, which is joint with a bunch of people, including me, about how to create better passwords for people. Yeah.
Thank you. Thanks for coming, everybody. Another similarity between this seminar and last week's seminar is that I'm going to be talking about user studies that were conducted online using Amazon's Mechanical Turk. But there will be a few differences as well, fortunately. I'm going to be talking about how to help users create better passwords. And in particular, we're going to be focusing on text-based passwords, the well-known and familiar password that you type in every morning whenever you try to access some Andrew service. There are lots of reasons why we don't like passwords. There's lots of talk of cooler replacements for text-based passwords, but I think we've all come to realize that text-based passwords are not going to disappear overnight. In fact, they're probably going to be around for a while. So at the very least, something that we should do, along with perhaps coming up with replacements for them, is to figure out how to best use text-based passwords. So I'm going to start out by motivating the problem a little bit more. What you see on the screen before you is a list of recent data breaches that took place in approximately the past year and a half. And the number in the right-hand column that you see is the number of passwords that was stolen during each one of these breaches. So these breaches, the passwords that were stolen might have been hashed or encrypted, but that still doesn't mean that they're safe, as I'll explain in a second. So something notable is not only that some of these numbers are pretty large, 25 million passwords is nothing to sneeze at, but also that some of the companies from which these passwords were stolen were not your random company that nobody's ever heard of, right? They were companies that we all know and trust and quite possibly have an account with. So this seems scary in itself. And in particular, what's scary about it is was described quite well by Jeremy White, the CEO of CodeWeavers, one of the organizations whose passwords got stolen. So he said, yes, it's true that the passwords are stored encrypted or protected in some other way, but with enough effort and depending on how good the password was in the first place, they can be cracked by an attacker who has stolen them in this encrypted fashion. So this means not just that if a password is cracked, it's not just the case that this particular account is vulnerable, but also possibly any account on which this user uses the same password. And we all know password reuse is something that occurs very frequently. So that really makes this kind of problem particularly troublesome. So what does an attacker do once he steals a bunch of passwords? And this kind of attack is known as an offline attack. So first of all, he has this file of passwords, each of which is hashed or encrypted. And what he needs to do is guess each of the passwords and then try encrypting or hashing each one of these guesses to figure out whether the guess actually corresponds to one of the passwords that was in the stolen password file. Now the question is, how does the attacker do that? He has many guesses, right? There's no limit to how many guesses he can try. This is not an online attack where something will stop working after 3 guesses or 5 guesses, right? He actually has all the data that he's guessing against. So he can guess as long as, for as much time as he's willing to invest into this. A dumb attacker might do something such as sequentially exhaust the space of possible passwords, right? So he might first try a password that's composed of all A's, then he'll switch one of the letters to B, then to C, and so on, right, until he has tried every single possible password in the space of possible passwords. This is not a very efficient method, and so that's not what an attacker does typically. What an attacker typically does is have some sort of understanding of which passwords are most commonly used by people, and he might have this understanding from having gained access previously to a large sets of passwords that have been stolen. He might have this access he might gain information about this by doing statistical analyses of those passwords, or perhaps just of words in the English language, to figure out what combinations of words or characters are most likely to be picked by users as passwords. And then what the attacker will do, he will order his guesses in such a way that the ones that he thinks are most likely to succeed are towards the beginning. Right? And in this way, the attacker is likely to guess a large fraction of the passwords from the password file he has stolen far, far more efficiently than if he were just enumerating them in a very naive way. So this is the kind of attacker we're worried about. And again, it is the typical kind of offline attacker these days. So what can we do to help things? Well, in the abstract, what we want to do is we want to help users pick passwords that are easy for them to remember, but hard for an attacker to guess. Right? And it's important that there's this trade-off here. We could, of course, force people to create passwords that are really hard for an attacker to guess, but quite possibly at the expense of making it also impossible for those passwords to be remembered, which kind of defeats the purpose. Of course, stating the goal doesn't necessarily bring us all that much closer to solving it, but here are 3 directions that we've pursued in trying to actually accomplish this. A common way of trying to solve this goal is for system administrators to adopt password composition policies. These policies are the sequences, the sets of rules that you see as you're creating a password that tell you what kind of password is legal in the system. And if you type in a candidate password that does not adhere to some of those rules, it'll be rejected and you'll be forced to create another one. It turns out that these policies aren't particularly well understood in terms of how much security or usability they provide, and so we spent quite a bit of time studying that. In fact, those of you who were at the talk that I gave at a CyLab seminar about a year ago will recall that I talked about this subject a little bit. I talked about this subject last year as well. So here I'll review a little bit of what I've talked about previously, but I'll try to do so only as much as is necessary for the rest of the talk to make sense. 2 more things that we've looked at are passphrases and password strength meters. So in passphrases, you can think perhaps of passphrases as a particular kind of password composition policy where the candidate password must in fact be a list of words, right? Possibly delimited by spaces or other punctuation. But it's not a password that looks at all random or it's not short. It's long and it's composed of a bunch of words that you can find in the dictionary. And finally, password strength meters are the little widgets that you see on the screen as you're creating a password that try to give you a sense for whether your password is good or bad. And again, this is something that there hasn't been much understanding of how well these work and what kind of features of meters make a difference. So before I get into the things that we've done, let me briefly talk about what kind of existing guidance system administrators can turn to when they're trying to figure out what kind of password composition policy to specify for their system. It turns out that a very popular kind of advice can be found in comics. What you see here is the XKCD webcomic that suggests that instead of picking a password that has many character classes, like the one here shown in the top left, one should instead pick a password that is composed of a bunch of dictionary words, and the XKCD comic argues that this password is both much more secure and much more usable than the random password, or more random-looking password. Now, this may well be true, but it's probably not the best idea for system administrators to seek guidance by reading online comics. Although, in fact, and perhaps sadly, a bunch of institutions, at least several institutions that have adopted a policy kind of like this, in fact, cite this comic on their university web pages as a reason for why they went to this kind of a password composition policy. There is slightly better guidance. In fact, the CMU policy, thankfully, is based on slightly better guidance. This guidance is in the form of a NIST document that talks about different kinds of rules you might include in your password composition policy, and associates each rule with a value in terms of bits of entropy that the rule will contribute to the passwords that are generated using a policy that includes that rule. It turns out, unfortunately, that although this guideline, the NIST guideline, is the non-comic book standard, it also is not one that's based on empirical evidence, and it's I guess a lot more grounded in science than the comic book is. But in fact, it's been produced by people who have studied passwords for a while, and then they came up with their with a set of hypotheses that they thought reasonably well represented how much each rule would contribute to the strength of passwords. And they're quite open about this, they don't have scientific evidence that supports their hypotheses. So what we wanted to do in the space of password composition policies is carry out a controlled empirical study of these different policies. And in the context of that study, we wanted to understand the effect of password composition policies on both security and usability of the passwords that were produced under them, as well as to try to make some progress on understanding what is a good methodology for actually talking about the strength of passwords. The methodology, what people have typically done is talked about them in terms of bits of entropy, but that's a measure that's come under attack, and it wasn't clear really how good a measure it was. So I won't talk very much about our data collection methodology because it really is quite similar to what Laurie talked at length about last week. I'll just say that this was a large online experiment using Amazon's Mechanical Turk. So Amazon's Mechanical Turk is this crowdsourcing service where if you are in need of somebody to do a little bit of work, you can publish the job that you want them to do, and then you pay them a small amount. Amazon helps match up the people offering jobs to the people seeking jobs, and it makes it easy for those offering jobs to pay people without ever learning who they are, and in fact also to get in touch with them later, again without necessarily knowing their name and email address. This is something that we used in this study. So the general format for the data collection, both for this study on password composition policies and the next two directions that I'll talk about, is as follows. We got people to come in, and they were, when they started the study, they were randomly assigned to one of a number of conditions. In this first study, in each condition, users were exposed to different password composition policies. Right? In the future studies that I'll talk about, people were exposed to different things depending on what we were trying to study. So we did not tell people that our purpose here was to study passwords or password composition policies. We told them a story that involved them pretending that their email account had been hacked, and their email service provider was requiring all users to change passwords, and they were asked to create a new password under some password composition policy, and then treat that password as they would their normal password. Then they took a survey, and we verified that they could recall their password. After that, there was a 2-day break. So 2 days after completing this first part of the study, participants got an email, and again, this was through Amazon's Mechanical Turk, so we could send the email without knowing who these people actually were. And that email invited them to come back, take another survey, and get an additional payment. And the purpose of coming back is that to force people to log in again so that we could verify whether or not they were able to recall their password, not just immediately after creating it, but several days later. So this methodology gave us access to a large body of plaintext passwords, in addition to all the data that we might have found out through the surveys and data that we could record while people were entering or creating the password, right? So things such as how long it took them to enter the password, how much time there might have been between keystrokes, how many keystrokes were required to enter a password, and so on. Through the surveys, we also got self-reported data about sentiment and about whether, for example, they stored the password, and if they stored it, how they stored it. And this is data. Some of this data also, again, is backed up by what we can measure. For example, people might lie when they tell us whether or not they wrote down the password, but we can still detect whether or not the password was copy and pasted into the password dialog box. And it turns out there was a lot of correlation. There was very good correlation between the self-reported data and the measured data. So we have good reason to believe that people were being honest. In a little bit more detail, we have 2 sets of metrics that we want to apply to these passwords. The first set of metrics has to do with quantifying their security. And here, when we look at the security of passwords, we measured it in 3 different ways. The first way is using these NIST estimates. These are based on the guidelines in this NIST document that I mentioned, where you essentially each rule has a particular value in bits of entropy. You add up all the the values associated with all the rules in your password composition policy, and that's how many bits of entropy your passwords are supposed to have. The second thing we did was actually, since we had the plain text passwords, we could compute an estimate of the entropy of that set of passwords. In fact, of the space of passwords gathered in each of the password composition policies. And finally, we looked at the guessability of the passwords to an attacker. So what an attacker would do is get some sort of password cracking tool and fire away using this tool at the password list that he has stolen. And this is something that we try to emulate, and I'll talk about this a little bit more. Yes?
What do you mean by, on the previous slide, you had this reported sentiment? What does that mean?
This is when we ask people about how much they liked X, or how annoyed they were by X, or how fun they found it, or how difficult they found it. That kind of thing. Yes, the password composition policy, yes. And again, this is backed up by data that is not self-reported, but is actually measured, such as how many people, how long people took to do things, how often they succeeded, how often they failed, how long it took them, and so on. Yes?
Another question. Why would they try to get a good password? To get a good password, or just the?
Right, so the question is, did the users have, did the participants have any incentive to get a good password? Yeah, there are a couple of answers to that. One is that we put them in a scenario where we told them that what they were trying to do is what they ought to do is pretend that their email password had gotten compromised, and they should create a password ostensibly for the purpose of protecting their email account. We've done some experiments previously which suggest that this kind of role-playing scenario actually makes a big difference in how people behave, and that in fact it's quite successful at causing people to behave pretty closely to how they would behave in practice. And there's also a lot of outside research that speaks to this. Okay, so I'll talk a little bit about measuring guessability, since that's a way of quantifying strength that we're particularly interested in exploring. When an attacker typically when an attacker gets a set of passwords, or when a researcher is trying to understand how strong a set of passwords is, what they would do is they would take these passwords, they would just feed them to a password guessing tool. There are a bunch of password guessing tools out there. A popular one is called John the Ripper. This is actually something the system administrators will do relatively regularly. They'll learn this cracking tool. Eventually, and eventually might take a while. It might take hours. It might take weeks. It might take months. The password guessing tool will spit out a bunch of plain text passwords. So some subset of these will have been spit out as plain text passwords, and then we'll just in this way we will just know what fraction of the passwords from the ones that were hashed or encrypted was crackable in that amount of time. Now, this approach has a few disadvantages. One is it can take a really long time, and one of the problems with taking a really long time is that you can only really do it once or twice. You can't take a few weeks or a few months of time very often. Unfortunately, that doesn't work really well because, as I said earlier when I was talking about these kinds of attackers, they try to order their guesses based on what they think are the most likely passwords, right? Most likely passwords to be found in the set of passwords they're trying to crack. And to do this, they use some sort of outside knowledge, right? So all of these tools are parametrized by outside knowledge in some way, right? And since we don't know exactly which body of outside knowledge an attacker is going to use to parameterize his tool, really to understand how resistant a set of passwords is to guessing, we ought to try different sets of training data for setting up this tool before we start cracking, right? But then the fact that it might take 2 weeks or 4 weeks or a couple of months to do the cracking is particularly troublesome because we certainly can't afford to take that much time times 10, say, to explore different ways of parameterizing the tool in the first place. So we came up with another way of doing this. Oh, sorry. So just to give you a sense for how long this might take in time and not in terms of just number of guesses. Um, this is only ballpark figures because they depend hugely on what algorithm is being used to hash the passwords and what kind of hardware you're cracking them on. But you could make, for example, 1,500 guesses if the hashing algorithm were SHA-512. So 1,500 guesses per second, or 130 million per day, or maybe you could make 2 billion per day if a different hashing function were used. And if you're using a GPU or a set of GPUs, you can do even more. So you can do maybe 30 billion guesses per day if the passwords are hashed using MD5. So a small lesson here is it might behoove system administrators to use a slow hashing algorithm to hash passwords before they're being stored, because of course the cost of hashing a single password once is trivial, no matter how long it takes. But to an attacker, the difference might be pretty substantial, since the attacker will have to repeat this process many billions of times.
Very parallelizable.
Sorry? It is very parallelizable, yes. Yes. So the more cores you have, the more dangerous you're going to be as an attacker, absolutely. So let me talk a little bit about this password guessing calculator that we built as an alternative to using password guessing tools. So here the idea was, instead of feeding the hashed passwords into the tool and having the tool spit out the plaintext passwords, we built a calculator to which we would feed all the plaintext passwords that participants would create, and the calculator which sort of understood how various password guessing algorithms worked. What it would do is just compute how long each plaintext password would take to be cracked. And it turns out that this is something that we could do drastically more efficiently. So after this tool had been properly trained, it would spit out these guesses pretty much instantaneously. And so we could, in the end, do many more experiments with different trainings of this password guessing calculator and get far better resolution in terms of when passwords would be cracked than we would be able to if we used the password guessing tool. Right. So let me talk briefly about the results that we've gotten in terms of the password composition policies. As I talk about results, I'll also talk about the specific password composition policies that we tested, and I'll talk about them pretty vaguely. If you're interested in more detail, feel free to corner me afterwards, and I'm happy to talk about it until your ears fall off. A lot of the results I'll present in terms of graphs that exactly like this one here. On the, let's see, on the y-axis, what you see is the percentage of a set of passwords that has been cracked. On the x-axis, you see the number of guesses that it takes an attacker to crack this percentage of passwords. And this line represents how resistant a particular set of passwords was to cracking. So to give this a little bit more context, here are a couple of lines that represent how long it would take to crack some number of passwords in 1 second, 1 day, and 62 years. And here, if we look at the 1 day line, we see that for this particular set of passwords, about 42% of them would have been cracked after 1 day of effort by the attacker, or about a little bit more than 1 times 10 to the 9th guesses. This particular line corresponds to something that we call the basic 8 condition, where the password composition policy required passwords to be at least 8 characters long, but there was no other requirement. Now let me add in a bunch more lines. We focused on, in our initial experiments, we focused on 7 different password composition policies. At the top, you have this basic 8 policy. There's a dictionary 8 policy which admits as a password any 8 character or longer word as long as it passes a dictionary test. There is the comprehensive 8 policy, which is something very close to our CMU policy. That is, passwords have to have at least 8 characters, pass a dictionary test, have a uppercase letter, a number, a symbol, no more than 3 or 4 of anything, and some other bizarre rules that most people don't know. There was a basic 16 policy where the only requirement was that the password be at least 16 characters long. And then we had 3 different blacklist policies where the only requirement for a password was that it not be on a blacklist. And the three different blacklist policies differed from each other only in the size of the blacklist. So we went from a pretty small blacklist to one that was 5 billion words long.
Big question.
Yes.
What's the size of the sample set over which these experiments?
Yeah, good question. So in this particular study, each line corresponds to 1,000 passwords that were collected under each condition. And this is also, I talked earlier about training the password guessing calculator or tool in many different ways. And so this is for the training that gave the most advantage to the attacker. So there are many trainings which perhaps are reasonable ones where the attacker doesn't do quite as well. But overall, the takeaways, the top level picture is pretty similar. Yes.
For the blacklist, did they have any character lengths for that? Since you have like Dictionary 8, Comprehensive 8, Basic 8, and Basic 16, how long were the blacklists, or could they be of any length?
That's a good question. So I think we just did not have any character restriction for those passwords, and the blacklists themselves contain both 8 character words and longer ones. Okay, so a few things to notice on this graph. One thing that's interesting to notice is that, first of all, the choice of password composition policy can make a huge difference, right? If you look all the way to the right side of the graph and compare, say, the basic 16 policy to the basic 8 policy, you see that in one case, 13% of passwords were cracked, and in the other case, close to 60% of passwords were cracked. So this is a pretty dramatic difference. Right. Another thing that's interesting is if you look longitudinally, the performance of different policies is quite different at different points in time. Right? So for example, if we focus on Comprehensive 8 and Basic 16, which are the 2 policies which are the most resistant to cracking all the way at the extreme, all the way on the right side of the graph, and if we follow those lines further to the left, we see that this relationship between Comprehensive 8 and Basic 16 isn't always the same. So for example, Basic 16 is definitely the best all the way at the end, right? But there's a point not too far, well, somewhere near the middle, let's say, where in fact Comprehensive 8 is much better. It's much more resistant to guessing than Basic 16. So, well, one thing that this might mean is that if you are administrator selecting a password composition policy, you also need to take into account how strong an attacker you're particularly worried about. Or another thing it might mean is that, well, none of these policies is the right policy, and maybe a little bit more experimentation is needed to figure out one that is resistant to guessing from both by an attacker who will not have very many guesses at his disposal to an attacker who will in fact have quite a few. Another interesting point perhaps is this kind of strange behavior that there is an inflection point where the behavior, the resistance to guessing for different password composition policies changes significantly, right? So it's not just the case that you have to be reasonably aware of whether you are defending against a weaker attacker or a strong attacker, but you might also have to be worried about these specific points where suddenly some policy might start behaving quite differently than it was for a few guesses fewer. Let me just briefly highlight one particular usability result. These are the answers to 2 questions. The one on the left is creating a password for this study was annoying. The one on the right is creating a password for this study was difficult. And what you see is in the red colors are people agreeing with the statement. The green colors are people disagreeing with the statement. And what you see on the graph is that, well, roughly speaking, at the top are the policies that are most resistant to guessing. At the bottom are the policies that are least resistant to guessing. And you see that the policies that are less resistant to guessing are also less annoying. and less difficult. And the policies that are most resistant to guessing, that lead to passwords that are most resistant to guessing, are also more annoying and more difficult to create passwords in create passwords in this case. But in more detail, if you just focus on these two, comprehensive 8 and basic 16, you see that by both of these measures, on both of these questions, comprehensive 8 did worse than basic 16. That is, comprehensive 8 was thought more difficult and more annoying, even though if we look at the strongest attacker, basic 16 was the more secure one. Right? That basic 16, between these two, basic 16 was more resistant to cracking by a strong attacker. If we look at comprehensive 8 and basic 16 a little bit more, right, so I already mentioned that they're both more resistant to guessing than other conditions and less usable than other conditions. But basic 16 just generally beats comprehensive 8 in both dimensions. So it seems that at least for password composition policies, more secure doesn't have to mean less usable. That is, we might be able to, through carefully crafting a policy, we might be able to have one that's both reasonably secure and reasonably usable. Or another way of looking at it is if we're looking for passwords at a particular strength, we need to explore the range of policies that will give us that particular strength so that we can select the more usable one. And there's good hope that some of these policies will be much more usable than others. Yes?
Did you try to do these experiments all at once with all the password cracking tools, or did you try to see how the performance varies as you vary the cracking tools?
Yes, so we did a bunch of experiments early on to try to figure out which tools we would use to, which tools we would focus on, and we eventually settled on one algorithm as generally outperforming anything else we tested for under pretty much any conditions, and this was a version of the algorithm by Weir, which I think appeared in Oakland in 2010. So that one just did sufficiently better than anything else that we tested that after we discovered that, then we started focusing on that one. Yes?
Do you have any measures of uncertainty for these results?
We don't have measures of uncertainty for these results. We have we've done statistical significance tests that tell us when these results are statistically significant when we're looking at differences between conditions, but we don't have a result that would say that the 13% crackability generalizes to a larger set in this particular way. Yes.
So for the basic 16, did you limit the users to only 16 characters, or could they have longer than that?
They could have the limit. The restriction was that the passwords could not be shorter than 16 characters, so they could certainly have longer passwords. Yes. Okay. Let me keep going. I'll very quickly go through this slide. This slide was the crown jewel of my talk last year, but it wasn't my talk last year, so don't want to belabor it too much. But what this does is it sort of connects the results that we got by figuring out how many passwords would be cracked using this guessing calculator to the empirically estimated entropy calculated from the plaintext passwords collected in each condition to the NIST estimates of entropy that were derived by following these NIST guidelines and adding up the entropies of the individual rules used in our conditions. So some things to notice here. One is that some conditions that are equivalent in terms of strength according to NIST, like comprehensive in 8 and basic 16, are actually very different according to entropy if we calculate entropy from the plaintext password that we collected. And again, then if you go back to the password guessing results that I just talked about, there's some similarity. There's some correlation between the guessing results that we got for a strong attacker and the computed entropy, but it's not. There are also differences. And of course, if you look further towards the weak attacker on the graph of passwords cracked, then the correlations between those results and either the empirically estimated entropy or the NIST entropy become even weaker. So what's the takeaway? Again, very briefly, I guess these existing measures, in particular, both NIST entropy and just calculating entropy directly from plain text passwords, if you have them, they're not totally worthless, right? They do give you a little bit of a sense for which password composition policies might be weaker and which might be stronger. Like basic 8 definitely was much weaker than comprehensive 8 according to any of these measures. But if you're looking at if you're trying to get a somewhat detailed understanding of two policies that perhaps are not so different from each other, then there seems to be little substitute for actually using a password guessing calculator or password guessing tool. Right. So that's more or less for the password composition policies. That's more or less what our findings are. This existing guidance is not particularly helpful, comic book or otherwise. I didn't talk about these policies. I didn't talk too explicitly about these policies being difficult to analyze, but we've done quite a bit of work just on the methodology of analyzing them. And it's interesting that there are cases where you can have both more security and more usability, so it doesn't have to be a trade-off. Any quick questions about this before I move on to passphrases? Okay, since I'm way behind time, excellent. So let me go back to this webcomic, because the webcomic is in particular suggesting that people use passphrases instead of passwords. And again, the idea is because you can associate some image or some story with these words, and they're words that you've heard before or used commonly. They'll be much easier to remember than something that looks like gibberish at a glance. And hopefully, or at least according to this comic, perhaps you even get more security out of it. Now, one difficulty is with evaluating the security of passwords like this is that the tools for doing so haven't been well developed, because of course so far people have mostly had short passwords, so that's what password guessing tools are good at guessing, and they're not very good at guessing long passwords. So if we were to point a password guessing tool at a long password, it might do terribly, but not necessarily because the password is good, instead just because the tool hasn't been optimized for trying to guess passwords like that. So here we tweaked things a little bit in how we arranged our study. So what we wanted to do is compare a bunch of different password composition policies, both to each other and to standard password policies that offer equivalent strength. But instead of doing what we did previously and letting people pick their own passwords and then trying to guess them, what we did to be able to precisely control for security is we assigned passwords to people. And because we were assigning from a space that we controlled, we knew exactly how much security was offered by each of the conditions. Now, of course, this might be a little bit different than how things might play out in many of the circumstances where we use passwords, but at least it gives us a good baseline for comparing the usability of the different password composition policies and the password schemes that we compare them to. Here are some of the specific questions we wanted to answer. We wanted to find out at high level, do people like passwords, standard passwords, better than passphrases, or vice versa? We wanted to understand how accurate or quick they were at entering one versus the other. We wanted to find out in detail which kind of passphrase scheme might work better than other kinds of passphrase schemes. And we also looked a little bit at error correction in terms of having an algorithm. Having an algorithm make up for users' tendencies to make typos when entering a password, which you can do with passphrases, but not as easily with passwords. So our conditions here had two classes. In one class of conditions, we had 3 conditions which were just passwords, and we had 8 conditions which were passphrases. We selected these so that we always had conditions of equivalent security to compare. We did try different levels of security, but we had always had a passphrase condition of equivalent security to a password condition, and then perhaps we had several passphrase condition which varied in exactly one factor, and all others were held constant. So let me go briefly through these. For passphrases, we had 3 conditions. We had random length 5 and length 6 passwords where the password was stolen. Password was selected from each character was selected from 64 possible ones. And then we had length 8 pronounceable passwords. This is pronounceable according to an algorithm that NIST recommends for generating pronounceable passwords. Your mileage may vary about how pronounceable you find these. Some of us found them not pronounceable at all. Some of us found them slightly pronounceable. But they're interesting because if we're talking about how to make passwords more usable, right? One extreme perhaps is passphrases, but maybe this is a small step towards making passwords not too different from what they normally are, but still more usable. So we wanted to look at that. In terms of passphrases, some of the core conditions were passphrases which were composed of 4 words, and we varied the size of the dictionary from which these words were picked. And in each case, these dictionaries were from a list of most commonly used words in English. So we were not picking really bizarre words that people wouldn't know. And you see examples of a passphrase from a small dictionary is find here, thing, give. From a large one is land, recent, describe, product. We also tried an unordered condition where it would be okay for a user to input the words of his passphrase in any order. So even though the assigned passphrase might have been set, almost, include, continue, it was okay to put in set, almost, continue, include. So to invert the last 2. We tried nouns only. So sense, child, reason, paper. Each word is a noun. We tried 3 words from one of the larger dictionaries, and we also tried a condition which was kind of sentence-like in that it was composed of a noun, a verb, an adjective, and a noun. So it results in passphrases like plan, build, sure, power, which doesn't quite make sense, but kind of sort of seems like it might make sense. Again, the thought for behind many of these is we were trying to explore which kinds of things are easier for people to remember. So I'm not going to go into the results in any detail here. The high-level result is this. The webcomic, maybe you shouldn't really listen to its advice. In a tiny bit more detail, there was no clear user favorite. The passphrases were slower to enter, and people tended to make more mistakes. And if you go back and think about it, actually kind of makes sense because passphrases are much longer than passwords. So if you have to type in 30 characters instead of 8 characters, maybe there's a bigger chance that you'll make more typos when you're typing in 30 characters. And we also found that in advantage of passphrases, there are places where you might be able to make up some of this loss in the inconvenience of typing it in, because you may be able to, in essence, do things like almost like just-in-time spell correction, right, and snap the small typo to the word that it should have been. And if you do this right, you can actually do it without loss of security. So on the one hand, passphrases clearly turned out not to be just the answer, the thing that we should all start doing immediately. But on the other hand, there were some positive signs about them as well. And one of the positive signs is that people didn't seem to be affected by how easy passphrases were to remember. Didn't seem to be very strongly affected by how large a dictionary each word was picked from. Right? So this suggests that perhaps it's possible to have passphrases which offer a far greater security than the passwords we compared them to, and maybe with only minimal loss to usability. So that's something outside of the scope of what we looked at, but it definitely seems like a possibility. Another interesting result is that these pronounceable passwords, which we kind of threw in on a lark, and I don't think any of us thought, or at least I didn't think that anything amazing would come out of it. These pronounceable passwords performed really well, so it seems like there's some promise in investigating pronounceable passwords more. Any quick questions on passphrases before I move on to the last segment? Yes?
When you did these experiments, what instructions did you give to the users?
So we gave similar instructions to the users as we had previously, amended in the smallest way possible to allow for the fact that the password is being system assigned instead of selected by the user.
And then you again tested after 2 days.
That's right, and they would come back. So the first day would involve the user retyping in the password several times. So both sort of immediately after it was selected, and at the end of the study administered during that day, and then 2 days later, users would get an email asking them to return, and they would return in the next couple of days after that, and all the results focus on the users that returned between 0 and 3 days after receiving the email. So basically between 2 and 5 days from taking the first part of the study. Okay, let me talk about password meters a little bit. I already said these are the little widgets that you see when you're creating a password, and their goal is to encourage people to create stronger passwords. Password meters are widely used. Lots of popular sites use them. I'm sure that that you've seen one before. Here you see examples from Google and Usenix, because that's where we published a paper on this study, and the WordPress blog. Even though they're widely used, there are many different designs. Right? They differ in how much information they convey, and how large they are, how colorful they are. So what we wanted to understand in a scientific manner, because apparently there was no such understanding prior to our investigation, is we want to see how password meters affect the guessability of passwords, how people put together passwords, like how they go about selecting a password, other details of the creation process, like how long it takes to create a password, the memorability of the resulting passwords, are they as easy to remember or harder or easier than passwords without meters, and also user sentiment. Do people love this, hate this? We also wanted to investigate in detail not just whether meters as a whole do this, but which kinds of meters have which properties. Are there some meters that work better than others? And if so, which elements of meter design are the ones that make a difference? And so what we'll talk about for the next few minutes is what we believe is the first large-scale experiment to answer these questions. And again, the data collection methodology here is the same as it was in the previous studies. Here again, we were back to a situation where the user is picking his or her own password instead of being assigned a password. We had a whole bunch of conditions in this particular experiment. They differed in ways that let them be categorized in the following 4 groups. First, we have several two control conditions. So one is where we have no meter, and one is with a simple meter. Then we have a bunch of conditions where the meters differ only in their visual elements and their visual characteristics. Then we have some meters that differ in how they score the password, and I'll go into detail there. And then there are meters that differ in both dimensions. We constructed our baseline meter based on meters that we've seen in the wild. In this particular meter, if you typed in 8 lowercase letters for your password, that would fill up 1/3 of the meter. And the meter would give you a high score either if you had a long password, like password, 16 characters, or if you included more character classes than just lowercase letters. So this is what the input screen, the screen looked like in which people were being asked to create a password. You see there's a meter here in the middle between the two password boxes. To illustrate a little bit about the meter, the baseline meter had a non-segmented bar. That is, the bar increased in small increments as your password became stronger. It gave you some feedback about how good the password was, and this every password starts out as bad and then it eventually becomes poor, fair, good, and excellent. And of course, not every password will be good or excellent or fair. It just depends on how strong the password is that the user creates. We give the user some feedback about how to improve his or her password, and sometimes we also give feedback that explains why the password is not a better password than as good a password as the user might think. Now, as the meter gets filled up, it changes color. It used to be red, now it becomes orange, and eventually, as the participant keeps typing, it becomes green. And if the participant types a strong enough password, then the meter gets filled up. But the participant need not fill up the meter entirely in order to create a valid password. The meter is just an encouragement to create a strong password. So here are the conditions which differed in visual elements. At the top at the top, you see the baseline meter. We had a 3-segment meter where the meter filled up in 3 increments. We had a meter that was always green, so there was no red, no orange, always green no matter how short. We had a small meter and a big meter. It seemed to make sense to me, at least, that if you have a gigantic meter, this would be more noticeable and perhaps people would pay more attention to it. And similarly, there are some meters that we observed in the wild that are really small, small enough that I thought I wasn't noticing them when I was creating my, say, Google password. We also had a meter which made no suggestions. So here, the visual part is the bar is the same as the baseline meter, but the text saying how the password could be made better is missing. And we had a text-only meter, which was just missing the visual component entirely, but it would still, in text, convey exactly the same things as the other ones were conveying. So as you see, as the user types, as the participant types in the longer password, you see how the meters, each of the meters looks. The green one is green. All the other ones have the same colors, and they all fill up at the same time. So now we also had one more condition that differed in terms of visual presentation. We sort of decided, well, there's so much fine-grained focus on these horizontal bars. Let's go with something entirely different. So we had a dancing Bugs Bunny, and here the better the password was, the faster the Bugs Bunny would dance, until at the end, if you made a really strong password, he would dance very vigorously. The conditions with scoring differences, again, the baseline is at the top. We tried one that always gave half the score that the baseline meter would give, so it was stricter. And then another one that was stricter yet. So this one gave a third of the score that the baseline meter would give. And you see that where the baseline is about 2/3 full, the 1/3 score is barely getting started. We also had meters that would nudge towards a specific kind of password. So we had meters that had a preference for long passwords, and we had a meter that had a preference for complex passwords in terms of many character classes. So if you had many character classes but a short password, this one would do poorly. This one wouldn't like your password much, but this one would, and vice versa. And then again, you see as the password gets longer now, although the baseline meter is filled out, the stricter ones aren't, and at the end, the 1/3 score is lagging behind all the others in admitting that this is in fact a strong password. All right, so I talked about what the metrics will be. I'll just show you a few snippets of the results. Again, some of the results will again be on a graph like I had previously shown, where on the y-axis is the percentage of passwords guessed, on the x-axis is how long it took an adversary to guess them, and of course the smaller the fraction that's guessed, the better, in that the harder the passwords are for an attacker to crack. So here at 5 times 10 to the 10th guesses, we have about 36% of the passwords in the no meter baseline condition being cracked. If we throw in the baseline meter condition, again, both of these are control conditions, we see that if we have the basic meter, that seems to do reasonably better than the no meter condition, even though in this case the difference wasn't statistically significantly different, possibly because our sample size here wasn't as large as previously. Here we had just hundreds of passwords as opposed to thousands of passwords that we were testing with. Now, here I threw in lines for all the conditions that differed only visually. Right? And what you see is they kind of cluster either around the baseline meter, or they actually tend towards the no meter condition, like the text only one and the green one tend towards the no meter condition. So the takeaway here is that, in fact, all these visual changes that we tried had pretty insignificant difference to guessing. Right? It didn't matter whether your meter was big or small or Bugs Bunny. It just kind of worked kind of like the standard meter. If we look at the conditions which change the strictness, however, we start to see differences. Right? So you see here the conditions which have stricter policies, they all, in fact, the lines indicating how resistant the resulting passwords are to guessing seem to indicate a greater resistance to guessing than either the no meter or the baseline meter. And particularly if we focus on the ones that gave 1/3 score or half the score of the baseline meter, we see a pretty substantial improvement, right? So here we're seeing at the end almost a resistance to guessing twice as good as it is for the no meter condition. And in fact, these results are statistically significant. In terms of memorability, we measured many things, but one of the ones we measured is how successful participants were at logging in both 5 minutes after creating their password and 2 or more days later. We also measured which percentage of participants in each condition actually returned 2+ days later to continue the study. And we measured how often people wrote the password down according to what they reported, as well as according to what we were able to capture by looking at their keystrokes. And in all of these ways, we found no significant difference across conditions in any of these metrics. When we look at self-reported sentiment here, what we're looking at is the question where people are reporting on whether the password strength meter was annoying. Let's see, we found that stringent meters were a little bit more annoying, and there came a time when people started getting angry at the stringent meters because they started behaving in a way that some participants didn't really understand what the meter was trying to do, and that the participant was convinced that this was a strong password, and if the meter didn't agree that it was a strong password, the participant might get fed up and decide that the meter didn't know what it was doing, and so then such a participant might start ignoring the meter. If we look at a graphical representation of this, so here again we're representing the participants' agreement with the question, the password strength meter was annoying. Red indicates agreeing, blue indicates disagreeing, so ideally we want to see more blue than red. And if we look at how participants answered in all the different conditions that we had, we see that if you look at the top half for all the conditions that different only in their visual features, there wasn't that much difference. There's a lot more blue than there is red. When we get to the meters which had different scoring strategies, in particular when we get to the strict meters, we start to see quite a bit more red. And you see here in the 1/3 score meter, not only is there more red overall, but there's actually a lot more of the deepest red than there is in the next most annoying condition. There were meters that we tested that were both strict and didn't have a visual component, and those really nobody loved. So what are the takeaways here? So meters definitely work, right? They lead to longer passwords almost no matter what kind of meter you try. Stringent meters help against these kinds of offline attacks. Possibly other meters too do, but that didn't show up in our study, maybe because of the smaller sample size. A nice thing which we weren't sure about is that meters don't affect memorability. That is, even though they're forcing you to create or helping you create a stronger password, they don't make for passwords that are harder to remember. And there's a limit. You can't just have a super draconian meter and expect usable and hard to guess passwords. When the meter becomes too strong, it seems like the benefits you get tail off and may even backfire when the users get frustrated and stop paying attention. In terms of specific features, scoring stringency was important, and having a visual component was important. What wasn't important was what the color was, whether the meter was segmented or not. The size of the meter was unimportant, and the bunniness of the meter as well. So just to summarize, I talked about several different directions that we've been pursuing, trying to figure out how to help users create better passwords. I talked about doing this through password composition policies, and one of those policies were passphrases. And I also talked about password strength meters. That's all I had. If you have any questions, I would be very glad to try to answer them. Thank you. Yes.
I wonder if the input device might factor into it as well. So if you have people who are, when the PlayStation Network hack happened, I mean, having to enter a very long password with symbols and everything on, a controller, for example, or on mobile devices, I would wonder how much that would affect the strength of the password and people wanting to keep longer passwords, like even on mobile phones, for example.
Yep. I think that's an excellent question. You could argue definitely that perhaps in a mobile phone. So everything that we did, we studied in the context of desktop computers. or laptops, but I guess non-mobile devices. You could certainly imagine that perhaps typing a very long password on a mobile device would be a greater disadvantage for long passwords than it would be if you had a full keyboard. On the flip side, you could also say that typing a password with more characters is more painful on a mobile device than on a full keyboard, but absolutely, I think this is something that's important to investigate. Yes.
Did you control for any kind of demographic or language skew in the Amazon users?
Yeah, so we certainly we have, I think, both. I don't remember whether we have self-reported demographic data, but we certainly have some demographic data from Amazon as well. And there are some differences. Like, for example, if you the two largest populations were people from India and people from the United States, and people from India tended to make slightly harder to guess passwords, but all the between conditions results seem to hold regardless of demographic differences. Anupam, did you have a question?
So do you have some understanding of the impact of this password composition policies on individual passwords? What I mean is, suppose that the password composition policy says we need capitalization, at least one capital letter or numbers. Do all the capital letters show up at the very beginning? Do all the numbers show up at the very
Yeah,
beginning?
we have a lot of results along those lines, pointing out explicitly what happens. I don't have slides for them handy, but I guess what are some interesting results from there? Certainly there is certainly the requirements are not fulfilled in completely random ways. So there is a tendency to put a symbol at the end. There's a tendency for that symbol to be bang or at. Overwhelmingly, as opposed to anything else. Numbers were interesting because it turned out that people were likely to use numbers no matter whether numbers were required or not, and they were used more evenly throughout the password. Also interesting was that the NIST guideline hypothesized very believably that people would fulfill the requirements in the minimal way possible. And we found that that's often not true. So we found that for passwords that had to be 8 characters long or longer, passwords were on average 10 characters long, which suggests that some people are going reasonably about.
Do the password cracking tools
Mhm.
that you use, do they take advantage of this background knowledge?
Yes. So the password cracking tools all the particular algorithm that perform best is one that does the statistical analysis of the patterns of some training set that you give it, and then it makes guesses based on that. So definitely one of the reasons why this guessing works well, unfortunately for attackers, is that the tool realizes that a number is most likely, or a symbol is most likely to be found at the end, and so it prioritizes candidates where the symbol is found at the end. Yeah.
One of the challenges seems to be that the password cracking attacks that the adversary use are seeded by background information, and it's not possible to know specifically what background information the adversary will have when he mounts the attack.
Yep.
As more data becomes available, like companies like RockU and Sony release more passwords, how do you see the efficiency of these attacks increasing, and how might that affect some of these security results?
Right. So yeah, so we experimented with this quite a bit actually, and so we have some results that I think I also talked about last time that talk about the importance of having training data that's closely matched to the password composition policy and perhaps to the user population that is being attacked. And so we found that for policies with many requirements, it was important to have closely matched training data. For policies with few requirements, it was less important, partly because in the absence of closely matched training data, attackers fall back on publicly available data, and that tends to be sort of general purpose and not data that resulted from complicated password rules. So I guess my sense from what we've done so far is that certainly attackers will become more effective. They won't become incredibly more effective, and I don't think any of the any of the results between conditions would be impacted by this. I think that the results the between conditions results we have still hold, and basic 8 passwords will be weaker than comprehensive 8 passwords, no matter how much training data an attacker has. Yes.
You present a story
Uh-huh.
to a public, but you didn't tell them the real intention. Is this acceptable practice? Academic
Uh-huh.
practice? That's the first question.
Yeah.
Secondly, when you do this kind of phony story, does that bias the reaction of the users?
Mm-hmm. So if anyone didn't hear this, the first question was, is it okay to not tell participants what you're really studying? And the second is, if you tell participants a phony story, does that bias the results? So yeah, it's okay to tell to fool participants. No matter whether you're fooling participants or not, you have to have your study approved by an institutional review board. And the institutional review board judges whether you're trying to do something that's unfair and shouldn't be done.
Again, all activities and after-school events for the Carnegie Mellon School District.
To your other question about whether the story biases results, absolutely. So we've tried the different kinds of stories. For example, we varied whether we were asking people to create a password for like a news website account versus an email account, and we found that participants created significantly stronger passwords if we told them that they were trying to protect an email account than if they were trying to protect a news account. But in this case, we see this as evidence of the story doing a good job of getting the participant to behave closer to how they would behave in reality. Okay, last question, yes.
Were the participants kind of like taught anything from the study, perhaps saying something like, for example, when you have these meters, you're kind of showing like, if this is the type of default password you use, this is probably not good practice. And also about, this is the thing that I try to like get into my friends' heads all the time is don't use the same password across accounts. Because, how many people do that a lot? And usually the consideration is I can't remember all these passwords, which is why like, I know that through other professors, they've mentioned like we should use passphrases so that you start thinking of things in words as opposed to I need to remember a whole bunch of gibberish with a bunch of symbols and characters. But, like kind of like did the participants realize that there was something to take away from it, or were they just looking to just do the stuff?
So we didn't go out of our way to say at the end of the study, by the way, do X, Y, and Z in order to be safer. But we did find that we gave participants an opportunity to give us some free-form feedback at the end, and quite a few participants said something like, oh, thank you for this. I never realized that my password was so insecure, or something along those lines. So it seemed like that quite a few people took away something constructive from the study, yes.
I especially wonder, too, if they use the same password that they use on actual sites for the study, too.
Right, yeah, we did explicitly ask them not to do that, and we did not try to determine how many of them ignored our instructions. Thanks very much for all the great questions. You guys were a good audience.